Well, we've been leading all semester up till today, the final quiz. Woohoo! Now, one word of warning, there's two incredibly beautiful topics that aren't actually on the final quiz because the final quiz was designed to be taken before Dead Week, and there are some topics that would fall in Dead Week, and that's the divergence theorem and Stokes theorem. So make sure you practice some problems. There's some examples of problems online. We'll probably get a little bit of a chance to talk about this in the future as well at some point. But now we're in our home stretch. 10 problems to go. So let's get started. So number 1. We're given a wire which is bent in the shape of a helix, sine of 3t, cosine 3t, 4t, where t goes from 0 to 2 pi, and the density of the wire is z. So in other words, what's happening? Well, we can imagine that we have the picture. We kind of know what the helix looks like. Now, if you see the sine 3t, cosine 3t, that's going in a circle. It actually goes clockwise, not counterclockwise, because it's sort of reversing the role of sine and cosine. Normally it's cosine sine. That's okay, it doesn't matter. So you have this sort of circular motion in the xy, and then z, it's moving straight up. So it's circling, going up. Now, because of the factor of 3, normally 0 to 2 pi is 1 revolution, but because of the 3, it's actually 3 revolutions. Now, all of these facts are not important, but that's just because we want to add some color commentary here. So we're going to go around once, twice, 3 times the circle, right? So that's our curve. So what happens is that our density is increasing as we move up in the z direction. So it's more dense near the top, less dense at the bottom. So our goal is to say, well, what's the mass? Whenever you're looking for mass, you always have the same formula in the back of your head. So the way we find mass is we add up density. And, well, really add up density times the proper measurement. Now here it's a one-dimensional thing, so it's one proper measurement is length. So we can write this in particular as mass is the integral along our curve of our density and ds. And ds is a shorthand for little piece of length. Well, all right. So in particular, it's the integral along our curve of z ds. So we got to figure out what's happening. Well, the way we do every integral is we're going to transform it into some integral we can do. So usually it's a iterated integral. In our case, we're going to write everything in terms of t. So 0 to 2 pi. Well, what is z going to be? Well, z is 4t. So that's cool. So 4t. How about ds? Well, ds, the way you find that, that's the square root of your x prime squared plus your y prime squared plus your z prime squared dt. So, what will that be? Square root of, now, take the root of x, you're going to get the root of sine is cosine, 3t, and then there's going to be 3 out in front. So when you square that, that's going to be 9 cosine squared 3t. Come here, derivative of cosine 3t will be negative sine of 3t, then times another 3, because there's a chain rule. So you square that, you'll get 9 sine squared of 3t. Z prime, oh, that one's nice, 4. Square that, you get 16. Well, what do we have here? Well, notice 9 times cosine squared plus 9 times sine squared is just 9. 9 plus 16 is 25. And square root of 25 is 5. This is one of the reasons why we like the helix. It's because when we talk about the little pieces of curve length, it turns out to be very nice. At least if you're using a really reasonable parameterization, namely with one involving the sines and cosines. So ds is 5 dt. So Well, that's an integral we can actually do. So if I integrate this, it's 20t. So the integral of that would be 20 over 2, which is 10, t squared. And then we're going to evaluate that from 0 to 2 pi. Well, 2 pi squared would be 4 pi squared. Don't forget the 10, which gets us 40 pi squared. And they didn't give us any units, and so that's it. Now, of course, we should also plug in 0. When you plug in 0, you get 0. So that's our final answer. 40 pi squared. Well, that's a good, nice one. Hopefully they stay that nice all the way through. Okay, number 2. Evaluate the integral along the curve x cubed plus y ds, where c is the curve given by x equals 3t, y equals t cubed, and time goes from 0 to 1. Well, the way we do line integrals, at least for now, is we say, well, what could this be? So the integral along the curve of x cubed plus y ds will become, put everything in terms of t, 0 to 1. X cubed. So x cubed, we're going to cube that. That'll be 3t quantity cubed. So that's 27t cubed plus y plus t cubed. Now we're not done yet. Now we have the ds. That's going to be the square root of, we take x prime, so that'll be 3 squared plus, take y prime, which is 3t squared squared. And then we're going to do that dt. Well, what do we have? Well, we can simplify some pieces here. We've got the integral of 0 to 1. These are both t cubed, so that's 28 t cubed. Then we have the square root of, and here both terms have a 3 that's being squared, so I can factor that 9, that 3 squared is 9, times 1 plus t to the 4th dt. Well, square root of 9 is 3, so I can pull that out. And then we have 28 times 3, which is some number. Well, okay, we'll see what it is. I'll write it as 28 times 3, and we'll deal with it later. Integral 0 to 1, and alright, so we have t cubed, and I'll write it as 1 plus t fourth to the 1/2. That's kind of a calculus thing to do. When you have a square root, you think of it as to the 1/2 power. Now, how do we make progress here? Well, the way to make progress, because this is not one of our 10 basic integrals, is to say, well, you know what? If I think of this as my inside, the derivative would be a t cubed involved. And there's a t cubed here. So this is set up to work really nicely with substitution. Almost like they wanted it to be something that works really nicely with substitution. Because they did. All right, now there's a 4 here. There's a couple ways to deal with it. I like to use the method of move the 4 to the other side. So 1/4 du equals t cubed dt. So what would we have if we do all of this? We'd have 28 times 3. Then we're going to get a new 1/4. And we'll point out where that 1/4 comes from. Then we have the integral. See, the 1/4 du comes from t cubed dt. So then there's a du. And then there's a 1 plus t to the 4th to the 1/2 is u to the 1/2. All right. Anything else? That's right, we've got to do the bounds. Don't forget the bounds. Now, our original bounds were from 0 to 1, but these bounds are in terms of t. We want to update our bounds in terms of u, because once you update your bounds, you always move forward. You never have to go back. When you plug in t equals 0, what do you get for u? You get 1 plus 0, which is 1. When you plug in t equals 1, you get 1 plus 1, which is 2. So now it's 1 to 2. All right. So let's do do just a little bit more work here. So we have the 28 times 3 times a fourth. And what's the integral of u to the 1/2? Well, that's u to the 3/2, because you add 1 to a half, multiplied by 2/3. All right. Now we're getting there. We're in the home stretch. And we need to evaluate this from 1 to 2. Well, let's see what we can do. The 3's cancel. Now 4, I can cancel with the 2, and then I can cancel a little bit more with 14. So we really have 14 times u to the 3/2. Evaluate that from 1 to 2. Well, that's 14 times 2 to the 3/2 minus 14 times 1 to the 3/2. Now the good news is 1 to the 3/2 is really, really easy. It's the kind of problem we like. It's just 1. 1 to a power is 1. 2 to the 3/2, probably the way to think of it is 2 to the 1 times 2 to the 1/2. So really we have 2 square root of 2. So if I take that and multiply it by 14, we end up with 14 times 2 root 2 is 28 square root of 2, and then on the other side minus 14. And that's our answer. All right, there you go. Now this was a case where we were able to handle our square root, not because we had a square or we had anything implicit inside of the square root, but because we had some other stuff in front. So there are cases where the line integrals, you can work with the terms on the outside to help figure out how to integrate. In general, line integrals are very tricky because of the ds. But we're going to see that in a couple of cases, coming up very soon, and it's actually not so bad. All right, let's try another problem. So, number 3. Find the work done by moving a particle along the curve C, given by f equals x cubed minus y cubed, comma xy squared, and the curve is x equals t squared and y equals t cubed, where t goes from -1 to 0. All right, so what's going on here? Well, the way you find work, especially along a curve, is you're moving along the curve, and then you have your, let me be careful here how I write this. It's sometimes written as f dot dr. I like to write it as m dx plus n dy, where m and n correspond to the pieces in your force function. So we have that as the integral along the curve of x cubed minus y cubed dx plus xy squared dy. So that's our integral. Notice this one doesn't have a ds involved. In some sense, that makes it easier because we don't have to introduce the square root. So how do we do it then? Well, the answer is we're going to write everything in terms of t. So this is going to become the integral -1 to 0, because our bounds are from -1 to 0. Everywhere we see an x, we put a t squared. So t squared cubed. Everywhere we see a y, we put t cubed. So minus t cubed cubed. Where you see a dx, put the derivative of x. Well, that would be 2t. Plus x, well, that's t squared. Y squared, so that's t cubed squared, and dy, the derivative of y, 3t squared. All right, so there's our x cubed minus y cubed dx plus x y squared dy. And then we're integrating that dt. So these kinds of integrals are pretty straightforward to set up. You just have to now be very patient and make sure you don't make a mistake, which is oftentimes the hardest part. So let's be very patient and let's work through carefully. So first off, t squared cubed would be t to the 6th power, because I multiply the exponents. This is going to have another 2t multiplying it, so that would be 2t to the 7. t cubed cubed, multiply, that's t to the 9th. There's another t making t to the 10th, so minus 2t to the 10th. That's the first part. Now the last part. Well, we have a 3. We have a t squared, t to the 6, because you multiply t squared, so that would make that 3t to the 10th dt. So we can actually combine because we have two things which involve t to the 10th. So that would be 2t to the 7th plus t to the 10th dt. All right, so far so good. Now what comes next? Well, next thing is we integrate. So here, the integral of 2t to the 7th, well, that would be 2 t to the 8, you add 1, divide by 8, plus t to the 11, divide by 11. And now we're going to evaluate that negative 1 to 0. So what does that do? Well, when you plug in 0, you're going to get 0 and 0. So 0, well, that's different, minus. Plug in minus 1. Now, for the first term, minus 1 to the 8th is a still positive 1, because if you have a negative multiplied 8 times, you get a positive. Then you have 2 over 8, which is really 1 over 4. Minus 1 to the 11th is a minus 1 over 11. Okay, so let's see, what can we do? Well, common denominator would be 44, right? So that's 11 over 44 minus 4 over 44. So here, 11 minus 4 is 7, but don't forget the other negative, so we end up with negative 7 44ths. And that's the answer. That's how much work is required to move. All right, and that's good. No, it's just being patient, knowing the formula, applying it, setting it up, and things work out. It's good. Now, next problem. Number 4. Find an f, so it's a little function, so that this capital F is gradient of f. So that's how we read it when we see the del thing times f. Now, one way you can think of this, if we think of it in terms of our language of functions, what we're saying here is that f is conservative, and when we're looking for little f, we're looking for that potential function. So, what does that tell us? Well, it tells us that the first piece here, that has to be the derivative of the function with respect to x. The second piece, which is kind of small, has to be the derivative of the function with respect to y. And then the last piece has to be the derivative of the function with respect to z. So now we're like, all right, we know what the partial derivatives are. Let's figure out what happens when we do the antiderivative sort of in each slot. So if I come to the first slot and I integrate with respect to x, what would we have? Well, so for right now, think of y and z as constants. So here, 2x, antiderivative of that would be x squared. So x squared y z. Derivative of 3x squared z, the integral of 3x squared z with respect to x. The z is a constant, integral of 3x squared would be x cubed z, and antiderivative of e to the x is e to the x. So that tells us our function has to have a piece that looks like x squared yz, plus a piece which looks like x cubed z, plus a piece which looks like e to the x, plus stuff with just out z. So that's stuff with y and z involved. So that's what our function has to look like just by examining our first slot. But remember, there's 3 slots. So let's go to our next slot. Take the integral with respect to y, because that's with respect to y. Treat x and z like a constant. So for example, x squared z. the antiderivative of that would be x squared yz. I'm just putting it in order of the symbols just because that makes it easier to read in a few minutes. Antiderivative of y would be 1/2 y squared. And then, what do we have? Then everything else. But everything else is stuff with xz. All right? So that's what we know. Take the derivative with respect to x. So if we know the derivative with respect to x, we have a good idea what the function looks like, up to stuff with just y and z. And similar in the second entry, we know what, if we take the integral with respect to y, we know what it looks like, up to, again, some lack of information for stuff because of x and z. Now if we come to our last slot, again we do the same thing. We're going to take the integral with respect to z. What do we get? Well, the first one, x and y are constant, so it's x squared yz. X cubed is a constant, so x cubed z. And then the antiderivative of 1 over 1 plus z squared, well, it wouldn't be a proper calculus quiz if we didn't mention it. That's arctangent of z. And then plus stuff. Now what's this stuff? This is stuff with x and y. So what we can do now is we start saying, let's piece our function together. So what will our function have to have? Well, as long as it has multiple variables, it has to show up consistently. So for example, x squared yz, that's good. It shows up in all the places it would need to show up. The x cubed z would need to show up both for x and for z, so that's good. And now the e to the x, it's okay that it's just here, because the only time it will show up is when we do e to the x. Then the half y squared, and the arctangent of z. So those are sort of, since they are expressions which only involve one variable, they'd only show up in one piece. Functions that involve two variables, or pieces of functions that involve two variables, show up in two pieces, and pieces that involve three show up in all of them. Now, the question is, find an f. You'll notice that this is a very carefully phrased question. It didn't say find the f, because is there a unique f? Well, it turns out, no. There's many. Now, how do you get the rest? I think you know where this is going. Plus c. Do you need the plus c? No. You see, because if you're just looking for one, what you do is you just say, I'll pick the one where c equals 0. Because oftentimes it's like, when you're thinking in terms of calculus, it's like, oh, I'm going to find the antiderivative to apply the fundamental theorem of calculus. I'll just find the easiest antiderivative to work with, which is when c equals 0. Okay, so that's number 4. Number 5. Evaluate the following line integral for c equals cosine t sine t, and time goes from 0 to 2 pi. So you have yz dx, xz dy, xy plus 2z dz. Now, there's lots of ways you can do this, and I want to be absolutely clear before we start that there's easily 2 different ways you could approach this. So I'm going to talk about one, and then I'll point out what the other one is. Now, when you're doing line integrals of this format, you should always sort of ask yourself a quick question: is this conservative? And if the answer is yes, try to use that fact. So what do I mean by use that fact? Well, what we're thinking of is, we're thinking of this here. This is our m, here's our n, and here's our p. So we have our m and p, and what we'd like that to be the case is that this is del f, because if we knew f, we'd be done, because we just have to figure out what's the function at the endpoints. Well, okay, so that says here's our derivative with respect to x. So we know that f sub x is yz, which tells us that f looks like xyz plus stuff. Now, how about f sub y? Well, that's xz. Well, that says f is xyz plus stuff. All right, that's good. And here, fz is xy plus 2z, well, that says f is xyz plus z squared plus stuff. And now we can examine our various potential functions for f and say, aha, we can use the function as xyz plus z squared. It is conservative, yes, because we found a potential. So, according to this is going to be, you take your potential function, xyz plus z squared, and you evaluate it from the start point and the end point. Now, what do we do first? Well, let's figure out the end point. So the end point would be when you plug in 0. So cosine of 0, start point is 0. Cosine of 0 is 1, sine of 0 is 0, and cosine 0, sine 0, 0. Now, 2 pi. Cosine of 2 pi, 1. Sine of 2 pi, 0. And then, why am I moving my finger there? Cosine 2 pi, sine 2 pi, 2 pi. Okay, so that's start and end. Now, from here, we're almost done. In fact, we're really close. So I'm just going to make some notes here. This is your start point. This is your end point. Just so when we look back at this later on, we'll be like, oh yeah, that's what we did. Yeah. It works. It's true. It's the true truth. So when we plug this in, what do we get? Well, we're going to get 0, because we have 1 times 0 times 2 pi, plus 2 pi squared. So that's 4 pi squared. Then we're going to subtract 0 plus 0 squared, which is 0. And that's the answer. And we're done. Now, I said there was another way you could do this problem. What's the other way you could do this? And it's not so bad. This is a case where it's probably almost the same amount of work. And that is to say, we could have just done what we did in the last problem. Namely, we'll say, look, everywhere there's a x, we're going to put the cosine t. Everywhere there's a y, we put in the sine t. And everywhere where there's a z, we put in t. So if we were to do that, and forgot to put my dz. So what would we get? Well, this would be integral 0 to 2 pi, and then we'd have y z dx. So that would be y is sine t, z is t, dx is minus sine t. Then, what do we get? Well, we get plus x, which is cosine t, times z, which is t, times dy, which is cosine t. Then plus xy, well, that's sine t cosine t, plus 2t, and that's times dz, which is 1. And then we just need to integrate that, dt. Well, if you look at this is integral 0 to 2 pi. I have here, t is common to both the first two terms, so that's t, cosine squared t minus sine squared t, and plus sine t cosine t plus 2t dt. And cosine squared minus sine squared turns out double angle. That's cosine 2t. So, integral 0 to 2 pi of t cosine of 2t. Now, sine t cosine t, I'll point out, that's actually, you can use, that's 1/2 sine of 2t plus 2t. All right, cool, good times, good stuff, equals, ... Okay, and then you keep going. Now, can you do these integrals? Well, you can if you remember the product, not the product rule. Integration by parts, which comes from the product rule. You have to remember stuff. But if you remember stuff, it does work out. And at the end of the day, you get to the point like, oh, wow, amazing. We get the same answer as before. It takes a lot more work. Now, I'm not trying to dissuade you from doing more work. I think doing work is good. It helps improve your character. But you should keep things in mind. And one of the things is, we have these beautiful ideas. The integrals of conservative functions are wonderful. So look for them and use them as much as you can. As much as you can. All right. Number 6. Let C be the curve that travels on the unit circle counterclockwise from 1, 0 to 0, 1. All right. So we're starting here at 1, 0. That's our start. And we're going to go up here to 0, 1. That's our end. And there's our curve C. And we're traveling counterclockwise. And we want to calculate the integral along the curve of 2x e to the y cosine x squared minus y dx plus e to the y sine of x squared plus x dy. Now we say, well, our mindset. It would be nice if this was conservative, right? Well, let's see. If it was conservative, we would say this part here, what would be the integral with respect to x? Well, we can kind of make it out, because you have a cosine of x squared. If you think of u equals x squared, you get a 2x. So it's kind of like the integral of cosine. So the antiderivative here would be e to the y sine of x squared. So if I integrate the first piece with respect to x, and if you're not sure about that, think about taking the derivative now with respect to x. E to the y is a constant, so it'll just stay as it is. Derivative of sine is cosine of x squared times the derivative of x squared, which is 2x, minus xy. On the other hand, if we took the antiderivative here, well, that's even easier. That's e to the y sine of x squared. And then here, it would be plus xy. Now, good news, bad news. What's happening is that we should be seeing what the potential function should look like up to missing pieces. Parts of it are good news. This is happy stuff for us. They match. So that means that parts of it are conservative. But other parts don't match. And when you have things which don't match, that means that parts of it are not conservative. Now the question is, what do you do? Do you give up and say, all right, we're just going to integrate everything along the curve put everything in terms of our parameterization? Or do we do something else? Well, here's the great thing about integration. Integration, you can break up. So what we can say is, hey, let's really think of this as two integrals. So I'm going to do the integral along the C, curve C, 2x e to the y cosine of x squared dx plus e to the y sine of x squared dy plus the integral along our curve of minus y dx plus x dy. Now, the first part, this is conservative. Now, why is that? Well, if you look, they're both, this is the derivative of e to the y sine x squared with respect to x. This is the derivative of e to the y sine x squared with respect to y. So in particular, we get that this is e to the y sine of x squared from the start point, 1, 0, to your end point, 0, 1. When we plug in at the end, so this is x equals 0 and y equals 1, we're going to sine of 0 times e to the 1. Well, sine of 0 is 0 times e to the 1 is, well, 0 times e is 0. So this is 0 minus, then what do you get here? Well, you get e to the 0, which is 1, times sine of 1 squared. So that's minus sine of 1. Okay, so that's from the first piece. Now, for the second piece, what do we do? Well, now we say, look, it's not conservative, so we can't use the tools. But let's not use the tools. We've simplified it. We have the part that's left is a lot easier to work with. What we don't have is a parameterization. So coming over here to this picture, we say, well, what's the parameterization that goes on the unit circle counterclockwise, starts at 1, 0, and ends at 0, 1? Well, the easiest parameterization is the cosine sine. That's really what's built to describe the unit circle, is that cosine sine. And we're only doing the 1/4 of the unit circle, so that says that our time goes from 0 to pi over 2. So this will become integral 0 to pi over 2. So we have minus y, so that's minus sine t, dx, the integral of cosine is negative sine, plus x, which is cosine t, times dy, which is cosine t, and dt. Well, we really have sine squared plus cosine squared. So that's the integral from 0 to pi halves of dt. So the part that wasn't conservative was beautiful, almost as if they wanted it to work out nicely. So this becomes t. Evaluate that from 0 to pi over 2, which is pi over 2. Now, the final answer says put your two pieces together, and so what we end up with is pi over 2 minus sine of 1. And that's the final answer. Nice. Cool. All right. Number 7. Okay. So, let C be the curve cosine pi t squared plus t to the 17th, comma, e to the t times 1 minus t minus sine of pi t over 2, where t goes from 0 to 1. All right. Now, you might notice something about this curve. There's a technical description we have for this, and it's called ugly. Now what that means is that this is a curve that's very unpleasant to work with. So that really is a sign, and the sign is don't use it. So we want to find a way to not have to use the curve. So we're like, okay, our goal is not to use it. Now, what are we doing? Well, so we have this ugly curve, and we're saying our function f is 3y squared plus cosine x plus yi minus cosine of x plus yj. And we're asked, find the integral along the curve f dot n ds. All right. Now, be careful here. I'm going to point something out. This is dot in n. It's not dot t. Now, normally we're used to doing f dot t. F dot t says what? Well, that's the amount of work to move along the curve. What does f dot n do? We don't need to know this, but if you're curious what f dot n is doing, it says if you have some curve c, so here's a curve c, then what you can think of is you can think of f as a vector field, and so what's actually happening is what you're measuring when you do this is you're measuring the amount of flow. So I can think of the f as modeling a flow, like a fluid flow. And I want to say, along the curve C, how much is flowing through that curve based on the flow modeled by f. Now, the first reaction is, well, if it's an ugly curve, we don't want to use it, it better be something conservative. So, let's ask our question. Is f conservative? Well, how do you check? Well, there's actually a really easy check. So remember the easy check. If this is m and this is n, one thing that has to be true about conservative functions is that m sub y has to equal n sub x. Well, does it? Let's check. M sub y, that's 6y, and then take derivative with respect to y, that's minus sine, derivative of cosine is negative sine, of x plus y. Does this equal, okay, come over here, take derivative of this with respect to x, Well, we're going to get a minus, so that's going to be a positive sign of x plus y. And you'll see these are not the same. So is the function conservative? The answer is no. But now you're thinking, but wait, we said it was ugly. And if it's not conservative, we have to embrace the ugliness, right? Right? Okay, now here's the subtlety. Here's the subtlety. It is 100% true that this function f is not conservative. But remember, it's f dot n, not f dot t. So f is the wrong thing to check for conservative or not. Let's work the integral a little bit. So we have the integral along the curve of f dot n ds. Now we're told what n is, so that's going to make our lives a little bit easier. So I'm going to think of this as the integral along the curve, and I'll write down the pieces. 3y squared plus cosine x plus y. So there's my comma minus cosine x plus y. I'm just writing it here. There's my f dot n. Now, if I think of n ds, I can think of the ds as canceling. So dy comma minus dx. So remember, the dot t ds would have dx dy. So if we do a little bit of rearranging, so I'm going to take the dot product here, that would be cosine of x plus y dx, because two minuses make a plus, and then plus 3y squared plus cosine x plus y dy. Now, this is really more along the lines of what we're looking for in terms of conservative. So what we're asking is the following question. We're wondering, is there some function where this part right here, we want this to be f sub x, and this part to be f sub y. See, it's a little bit different. See, previously it's like, oh, we wanted that part to be the derivative with respect to x. But they've changed roles because of the fact we're doing dot n. So that's why you always have to be really careful. So the first part says here, f really has to look like sine of x plus y plus stuff with y. Because that's what the first piece says. The second piece says, hey, our function has to look like y cubed, taking the antiderivative with respect to y, plus sine of x plus y, plus stuff with x. And now we see, okay, there's no contradiction like we had before. Lo and behold, this is a conservative function. I can use the function y cubed plus sine of x plus y. And that works. So we get the following. This is equal to, we take the potential function y cubed plus sine of x plus y. And now, the last part is we need to evaluate this. So let's figure out where we start and stop. So we're going to plug in time t equals 0. Cosine of pi times 0, so that's really cosine of 0, which is 1, plus 0 to the 17th. Well, that's 0. So you get 1 plus 0. So the x coordinate where we start is 1. How about here? E to the 0 times 1. So that's e0, which is 1, minus sine of 0. Sine of 0 is 0. So we start at 1 comma 1. Where do we finish? We'll plug in time t equals 1. You get cosine of pi, which is negative 1, plus 1 to the 17th, which is positive 1. Negative 1 plus positive 1 is 0, comma. Here, we'll get e to the 1 times 0, so that's e to 0, which is 1. Then we're going to get sine of pi halves, which is 1, but we're subtract. So 1 minus 1 is 0. So you might say, wait, is that right? Don't we normally start at 0, 0 and end at 1, 1? No. It always depends on the curve. You can start at any point and end at any point. Don't get too caught up in like, oh, 0, 0 should be before 1, 1. Because that's not the case anymore. We can start anywhere, we can end anywhere. So, what do we get? Well, we plug in 0, 0. Well, lots of zeros, so we're going to get zeros out of there. Minus, when we plug in 1, 1, 1 cubed is 1. Sine of 1 plus 1 is really sine of 2. Or we could write that as minus 1 minus sine of 2. And there's our answer. Good, good. Yeah, so this one, I put this on an exam a couple of years ago. A long, long time ago. This is like 4 or 5 years ago. And I told the students explicitly, there's going to be a problem that's going to involve a conservative line integral on the test. And they took the test, and after the test was done, there was no problem that involved a conservative line integral. You lied! And then they saw the solutions later on. They're like, okay, you didn't lie. Yep, you were right. It works out. So be careful, and pay attention. Small changes, that can have a big effect on what you're doing. So you don't want to get sort of, for lack of a better word, you don't want to be sloppy. You want to be careful, methodical, and work it out. So whenever they change something, you'll be ready. All right, number 8. Okay, ooh, this is already more interesting because we see the word region. That means it's two-dimensional type thing. So what is it? S is the region. X squared plus y squared is less than or equal to 1. So that says, well, something about a unit circle. We're inside a unit circle. And x plus y squared is less than or equal to 1. I don't know that one. Okay, but we'll get to it. We'll figure it out. Let C equal the boundary of S. It's the boundary of the region oriented counterclockwise. Find the integral along the curve C, y cosine x minus e to the minus x minus y dx plus sine of x plus e to the y dy. Now, what's the right technique? Well, we have a region, and it's oriented counterclockwise, and we're looking at the boundary. These are clues. So when you're looking at an integral along the boundary of a region, especially an oriented integral, that tells us Green's theorem. So let's take a look at it. So as a reminder, what does Green's theorem say? Green's theorem says the following. I'll sort of draw by picture here. So what you have is you have a region R. The boundary of R is your curve C. And you have, I'm going to shade my region here just for reference. Okay, so there's our shaded region. All right. Then what we have is that the integral along the boundary of m dx plus n dy is equal to the integral over the entire region of, and this is the part you have to think for a little bit, and I'm going to be a little bit cautious here because I want to make sure I get this right. And let's see, what will it be? I think it will be partial n partial x minus partial m partial y dA. All right. So there you go. That's Green's theorem. So this is important. We're going to put a little box around it, not because that's the answer, but because there's our big tool. The thing that makes it a little bit tricky is that the minus sign is there. So you got to remember which one comes first. The reason that you need a minus, in some sense, is because there's an orientation that comes into play. It matters which direction you travel your curve. And so there should be something that says, hey, sign matters. Sign is all about orientation. All right, so let's work on understanding our region. So we have a couple of things. So x squared plus y squared less than or equal to 1. That's easy enough. That says we're within the unit circle. Let's think about this x plus y squared less than or equal to 1. Now let's start by doing the equality. X plus y squared equals 1. Well, that tells us that either x plus y equals 1 or x plus y equals negative 1. Now, if you move the x's across, you get that y equals 1 minus x or y equals minus 1 minus x. Now, in terms of lines, these are lines which have a slope of negative 1, and you either have a y-intercept at 1, slope of negative 1, so you'd have that, or a y-intercept of minus 1, slope of negative 1, so you'd have that. They actually intersect at very convenient spots. Now that's x plus y squared equals 1 are these two lines. So it's chopped the plane up into 3 pieces. Which of the 3 pieces do we use? Well, let's just think about a point. So for example, if I choose the origin, that's in the middle piece. 0 plus 0 squared is less than or equal to 1. All right. If I choose a very large value, say on the x-axis, then x plus y squared will be big. So that says you don't include that part. If I choose a very large value negative on the x-axis, again, x plus y squared is big. We don't include that part. So that says we want to have the middle strip. That's what the x plus y squared less than or equal to 1 tells us. Okay, so our region, let me blow up our region. So it looks like the following. We have these 2 lines here, and then we have 2 quarter of a circles. And so here's our region, it's called S. And now our curve is oriented counterclockwise, so here is our curve. All right, we've made progress. We now have our basic setup. You're probably thinking, I don't know, you're running out of real estate on your paper here, Steve. Are you going to have enough space? That's a good question. I think I will, though. I'm very optimistic because oftentimes once you understand the setup, the rest of it is going to be quick. I'm going to go ahead and mark a few points here just for reference. So this is at -1, -1. All right. So according to Green's theorem, the integral along our curve of our expression here, y cosine of x minus e to the minus x minus y dx plus sine of x plus e to the y dy is equal to the integral over our region. Now we come to this term here, and we're going to take the derivative of this with respect to x. Derivative of sine x with respect to x is cosine of x. Derivative of x with respect to x is 1. Derivative of e to the y with respect to x is 0. Subtract. So that was our n sub x. Now we go m sub y. Derivative of y cosine x with respect to y, cosine of x. Derivative of minus e to the minus x with respect to y, 0. Derivative of minus y with respect to y is minus 1. We're going to integrate that dA. Now, nice thing happens here is that the unpleasant part, namely the cosine, they cancel out. Then what we have is we have a positive 1 subtract a negative 1, so we get really 2 integral over our region dA. Well, that's really, whoops, what did I say R? It should be S. Okay, S. All right, so this is really 2 times the area of S. Okay, well that's not so bad. Let's figure it out. So we just have to figure out what this area is. Now it looks bad, but that's if you try to think of it as a whole. Think of it as little tiny parts. So for instance, how about this part right here? How much area is there in that part? Well, it's a triangle. 1/2 base height. So how much area is there in that piece? Well, it's 1/2. How much area is there in this triangle? Well, 1/2, because again, same idea. Now, how about here? Well, this is 1/4 of a unit circle. The whole circle has area pi, well, it just has area pi, right? So this is 1/4 of that, pi. Same idea. Up here, this piece has 1/4 pi. So what do we get? Well, if we add up the areas, we're going to get 2. We have a half plus a half, which is 1. Pi fourths plus pi fourths, which is pi halves. And if you distribute the 2 through, you get 2 plus pi. And that's the answer. 2 plus pi. Woohoo! These are fun. I actually like Green's theorem problems. They're one of my favorite types of problems. And they're almost always going to be something where you have this integral and like, these are terrible things that we have to find antiderivatives for. But once you apply the theorem, because of the partial derivatives, things cancel out beautifully. And you end up with something which is a very straightforward integral, and then life becomes really clean. And it's good stuff. All right, that's number 8. Lots of green used on that page. How about number 9? Okay, so let C be the closed curve x minus 2 quantity squared plus y minus 2 quantity squared equals 1 oriented clockwise. Ooh, even they made it italicized, very fancy. And let D be the closed curve consisting of 3 line segments. All right, let's sketch this part here. So we have 3 line segments, and they're joining 0, 0, which is here, 6, 0, so that's, say, over here, and 0, 6, which should be up here. All right, so let's put those in. So we have 0, 0 goes to 6, 0. That goes to 6, 6. And then we go back to 0, 0. So this is actually oriented counterclockwise, and this part is our curve D. Now, where is C at? Well, C is a circle because we recognize it. X minus h squared y minus k squared equals 1. And it's centered where? Well, it's centered at 2, 2. So let's see. So 2 is roughly here and here, and it has radius 1. And so it's not going to go out very far. So it's actually, C is completely on the inside of D. There's no intersection, no overlap. Now this curve, we got to be careful because it's oriented clockwise, so it goes in the direction of a clock. All right, there you go. That's C. So now what's our goal? Our goal is find the integral along the curve C and D. So in other words, we're going to add up the pieces together. So what's the integral along this curve plus the integral along that curve of this big expression? Now, what do we do? Well, when you see closed curves in the plane, you should think of one thing, and that is Green's theorem. So we're not going to rewrite what Green's theorem is, but we're going to say this feels very Green's-like. So where's our region at? Well, our region is what's on the inside of the curve, but we have something going on here. We kind of have a curve within a curve. It's sort of like an inception of math problems, something on the inside. Well, what does that mean in terms of our region? The answer is it's actually kind of beautiful what it means. Notice the orientation. It's not just random. The outside, it's oriented counterclockwise. The inside is oriented clockwise. So what it is we can think of our region here as a big triangle, which comes from the outer triangle, plus a circle that's been punched out in the middle. So in other words, this is a holy region, a region with a hole on the inside. All right. Well, does Green's theorem apply to regions with holes? And the answer is yes, just as well. All we have to make sure of is that the orientation is correct. Well, how do you do the orientation? Well, you have to imagine that you're walking on the curve and you follow the orientation. So as you follow the orientation, where's the region? It's to your left-hand side. Good. That's the right orientation. Now how about on the inside? Well, on the inside, as we follow the curve, we would do along here. And again, orientation's on my left-hand side, so that's the right orientation. So there's the song that you remember. To the left, to the left. When you walk the curve, keep the region to your left. Good. So we have the right orientation. So according to this will be equal to, if we think of this, I'm going to do some shorthand. Here's m, here's n. This is going to be equal to the integral over our region of n sub x minus m sub y. Okay, so let's take these partial derivatives and see what we end up with. Integral over our region. Take the derivative here with respect to x. Well, the derivative of x e to the y with respect to x is e to the y. Derivative of natural log of 1 plus x squared. Well, that would be natural log is 1 over 1 plus x squared times the derivative of 1 plus x squared, which is 2x. All right, so there's our partial and partial x. Subtract, okay, m sub y. Derivative of e to the y with respect to y, e to the y. Derivative of y times x minus 1 quantity squared over 1 plus x squared with respect to y, well, almost all this is x stuff. There's only a single y, so it's all the x stuff. X minus 1 quantity squared over 1 plus x squared. All right, dA. Now the good news is, at least part of this is nice. You can see you have e to the y's, but because of the subtraction, you get cancellation. Now we have all this other stuff which is not looking very promising. We can say that the minus minus makes a plus, so that's something. And if we stare at it a little bit more, we say, hey, something else goes on. They both have a common denominator, 1 plus x squared. So you get the 2x, and then plus, well, x squared minus 1 quantity squared. Let's go ahead and expand that. That'd be x squared minus 2x plus 1. Oh, wait a second. Oh my gosh. Look at that. There's more cancellation. It's just like, it's the cancellation fairy, the gift that keeps giving. And whoa, wait, let's not stop there. Look, what do you see? X squared plus 1 upstairs, 1 plus x squared downstairs. This is the integral over our region of 1, dA. Now when you integrate 1 over your region, you get the area of your region. This is a two-dimensional area, so that's finding area. Sorry, two-dimensional integral, so that finds area. So we just have to say, well, how much area is there? Well, it's a triangle, so we think of it as triangle minus the circle. So the area of the triangle was 1/2 base times height, so 1/2 of 6 would be 3 times 6 would be 18. This is a unit circle, so if we think of the area of a unit circle, that's pi r squared. So the area of the circle is pi. So big triangle minus the circle, and that is the answer. 18 minus pi. Oh, wow. We should have all questions be Green's theorem questions, because they're some of the funnest questions to do. All right, that brings us up to number 10. It's like we should have a drum roll. Ooh, makes a little tremor. Okay, so imagine that we didn't do a drum roll. Wow, our last problem, our final one. We've been through so many together. It's been a long journey, but time to finish on a positive note. So, let G be the part of the surface z equals y squared minus x cubed lying above R, where R has x going from 0 to 1 and y goes from 0 to 1. Find the flux for this function f through the surface G, where n is the upward pointing normal. Now, your first reaction upon hearing this will probably be, because it's not so clear what's going on. So what's happening And I'll draw a very terrible picture, and because a terrible picture is just sort of to help us understand what's going on. We have a region in the xy plane. It's actually a really nice region. X to 0 to 1, and y goes from 0 to 1. So here's our region in the xy plane. So we have here, this is our R. And then there's this surface that corresponds to this function. Now, the picture here is going to lie to you about the surface, but that's okay because we're working for understanding, not for accuracy. So the lie is going to be that your surface is doing something kind of way above the region. In fact, this surface is going to sort of slice through the xy plane. But that's not important. So here's your surface z equals f of xy. And what you're looking for is when you're looking for flux, flux is a very fancy word which means flow. So what you have is you have a vector field, and a vector field can be used to model how things move through a system, like for example, how particles move through a system. So you have these particles which are moving through the surface. And the question is, how much is coming through? And that's what we're trying to find. So whenever you see the word flux, think of it as the word flow. Find how much is flowing through. You can think of it as electrical flow, water flow, wind flow, anything that moves, you can think of it as flow corresponding to that. So the way that this is done is you do the following. So to find the flux, that's the integral along your surface, so in this case it would be g, of f dot n d surface area. Now, this looks bad and looks complicated, but now some good news. There's a beautiful case that's actually very easy. So what I'm going to think of this is, I'm going to think of f as being some m n p. It's a vector valued function. I'm going to think of the surface as being something of the form z equals f of xy over a region R. Then what you get is that this integral on the surface becomes an integral over your region, and it's minus mfx minus nfy and plus p dA. All right, so that's what it's going to become. So if you haven't seen this yet, there will be a lecture on this, and it's a formula. And how do you know to use the formula? Well, you look for something that has a flux through a surface, and it's not just any surface, by the way. I should point out that it's an oriented surface. So here, when it's talking about the upward pointing normal, that says that, oh, it's not any surface, it's something where I have a top side. And so, okay, all right, we digress. So how do we finish this? After all, we must finish this one to add it to our great collection of problems which we solved. So let's figure out what this is going to become. Integral of our region of minus. Now we say, okay, we have our m. Well, what's m? It's right here. 2y arctangent of z squared. That's not looking promising because we got to integrate that. Okay, so that's our m. And then we're going to multiply that by f sub x. So here, this y squared minus x cubed, this up here is our f of xy. So f sub x would be minus 3x squared. Then we have minus our n, so 3x squared arctangent z squared times f sub y, which is 2y. And then we get plus our p, which is z. Now, the thing is, we want to have our region R, this is an xy region. How do I do z? Because z is not in terms of x and y. But now we remember, well, wait a second, we're on the surface. I can replace z by f of xy. So this will become y squared minus x cubed. And that integral is dA. Now at this point you're probably just like, how do we do this integral? This is not looking promising. But wait a second, maybe not all hope is lost. Minus minus makes that first term plus. What do we have? We have 6 x squared y arctangent z squared. Here we have 6 x squared y arctangent z squared, but with a minus. So, the first two terms cancel out. So it's set up so that, yes, the integrals themselves are absolutely atrocious. We'd never ever want to do them, but the problem has been set up in a way that we get something very nice. So it reduces to the integral of y squared minus x cubed dA. And I'll just put this as a reminder. This part right here is our z. All right. Well, let's finish this up. So we get the integral, and our region is 0 to 1, 0 to 1. So 0, 1, 0, 1, y squared minus x cubed. Doesn't really matter which one we do first, dy dx. So if we integrate that with respect to y, we'll get 0, 1, 1/3 y cubed minus x cubed y. And then we evaluate from y equals 0 to y equals 1 dx. Well, at y equals 0, we get 0. And when we plug in y equals 1, well, we're going to get 1/3 minus x thirds. So we integrate that, we're going to get 1/3 x minus 1/4 x to the fourth. And we evaluate from 0 to 1, that'll give us 1/3 minus 1/4, and then subtract 0. Common denominator would be 12. So 4/12 minus 3/12 gives us 1/12. And that is our final answer. 1/12. The final answer in our 12th quiz. Wow. What a journey it's been. We started this, for some of us, we've been here several semesters now working through these problems. And our last quiz problem. Well, thank you for sticking with it and for staying to the end. We appreciate you taking the time to learn the material because we are passionate. We do want you to learn this material and we want you to make sure you're setting yourself up for future success. Thank you for your time. Thank you for your dedication. Please take care of yourself and please make sure you put yourself in a good situation, mentally, physically, and to do well in the class. And I guess this is the end of our quizzes, and good luck. Take care. Bye.